Hi, this video builds directly on the previous video that introduced the concept of the singly linked list and defined how the structure works. What we're going to do is start covering the operations, and we're going to start with the constant time operations because they're relatively simple. So here are all of the operations we are going to cover on the singly linked list. You can create an empty linked list, get the size, get the front and back elements, push front, push back, that means add to the front, add to the back, and PopFront, meaning remove from the front. All of those can take constant time, and we're going to go over those in this video. There's some other operations that take linear time because they are more complicated. PopBack, meaning remove the last element, and get an element at index I or set the element at index I. Those take linear time. We'll cover those in the next video. So this video, again, is covering constant time operations. There's no iteration, no loop or recursion needed for these. So that's the operations that I listed. And first, let's look at the constructor. So the goal of the constructor is to initialize all the data members into a valid state for an empty singly linked list. On the right, we have a sketch of what this should look like after we're done. So we need a list object. Size needs to be the number 0. We need a tail pointer that points at a single node called the dummy node, and the dummy node has an element data member that we're going to leave unused. It's not holding anything important, and it has a next pointer that needs to point at itself. Now, there's a bit of a dilemma here, or a catch-22. We can't have dummy node initialized to have its data pointer point at itself because that pointer doesn't exist yet. So this has to be a two-step process where we'll create a dummy node and have its next pointer point at null, meaning nothing, just temporarily for a brief moment. Then after we've allocated the dummy node and we know what its address is, then we can set the next pointer to that address. So that's what this constructor does. We initialize tail to be a make shared pointer. So this allocates a singly linked list node. The element value is t open paren close paren. That calls the default constructor on type t. So that just creates a valid t object, and we don't actually care the value. We're not going to use it. And then temporarily for a moment, the next pointer of this dummy node is null. We initialize size to 0, and then the body of the constructor, as soon as we can, sets tail's next pointer to tail. So that creates this circular link. Let's look at the accessors. These are pretty simple. The size accessor just returns size, takes constant time. The back function has an error check. If the list is empty because the size is 0, then there is no back element and we throw an exception. But if size is positive, there is an element at the back. And we can get to that back element by following the tail pointer. That gives us a node object. And then we call the element accessor to get the value out of the node. So note that t back returns t. It doesn't return a pointer to a node. Our user doesn't care about node pointers and really shouldn't be able to see them. They care about t. If this is a list of ints, they want an int. So we follow the tail pointer, get the element there. That gives us a t. Front has the same kind of thing. We check that if the list is empty, you're not allowed to get the front element because it does not exist, and we throw an exception in that case. But if the size is positive, we want to get at the first element here. It's a little tricky to do that, but we can do it. If we follow the arrow here, we need to get to this node right here, and the list class only has one pointer into this thing pointing at the tail. So you go follow the tail. That gets us to the last node. The next of the last node is the dummy node always. That's an invariant on the list. And the next of the dummy node is the front node always. That's another invariant on the list. So the code ends up being tail, arrow, next, arrow, next, arrow, element. A little bit of a mouthful, but it's how it needs to work. Okay, now let's look at adding to the front of the list. This one's a little bit more complicated because it modifies things, and I'm going to follow my own advice here and make a sketch of what we need to do and a checklist of pointers. This is what I advise you do when you're writing this kind of code to make sure you don't overlook pointers. So let's do a concrete example. Let's say I have a list that contains 4 and 5. On the left is a sketch of that, complete with the dummy node and the circular link and the tail pointer. Okay, what needs to change? On the right-hand side is what that list should look like after adding the number 9 to the front, push front of 9. So size needs to be incremented to 3. Little detail, don't want to forget that. And there needs to be a new node, and that new node needs to be in the front position, which means it needs to be after the dummy node and before the old front. So before the 4 and after the dummy needs to be 9. That means we need to create this 9 node. 9's next needs to point at the 4 node, and dummy's next needs to point at the 9 node. So I see 2 pointers. There are 2 red arrows, dummy's next and the new node's next. We need to make sure that our code gets those 2 pointers pointing properly. So that's my checklist, those 2 pointers. Here's my code, and let's review how it works and then check my checklist. So first what I do is say shared pointer dummy is tail next. I could skip that and just always say tail next in a bunch of places, but this code is already kind of long and confusing. It helps the reader a lot to say what we're pointing at. So I just make a temporary pointer here called dummy, and dummy is a pointer to the actual dummy node, and the dummy node is always tail next. So my dummy pointer is pointing at the actual dummy node. And then now I make a new node, and that is make shared of a node containing element x. That's the passed in argument that we want to store. It would be 9 in the sketch here. And the next pointer of the new node needs to be the dummy's next. So let's look at my sketch here. When I insert the 9, we're going to put a new node there. What does this new node's next pointer need to be? It needs to be whatever dummy's next used to be. So dummy's next used to be 4. That's what the new node's next needs to be. So that's why I choose that there. That's one of the 2 pointers on my list. There's still one more pointer on my list, which is the dummy's next. So I do dummy set next to new node. If we stopped at this moment, the dummy node would still point at 4. That would break one of the invariants because dummy needs to point to the front node, not the second node. So we need to change dummy's next pointer. It doesn't point at 4 anymore. Now it points at this new node I just allocated. Finally, plus size just increments the size so it's accurate. Okay, so I think this checks out. It does address the 2 pointers on my checklist. You can notice it might have been easy to overlook one of those if we weren't being so careful. This takes constant time because these are all constant time operations. There's no loop. Now let's look at PushBack. This is a pretty similar operation, so I'm not going to go into quite as much detail. In PushBack, we're trying to add a new node to the back of the list. So we want to add a new node object in the right place, which is after the last node and before the dummy node. In between those 2, that's where the new last node needs to go. So the code is kind of similar. I allocate a new node, which is allocated to have a node object with an element equal to x, which is the passed in value. So that's 9 in the sketch here. And the new node needs to have a next pointer, which is tail next. Okay, so tail next is another way of saying the dummy node. If we look at the before sketch here, tail would have the current last node, which holds a 5. Tail next is the dummy node. And I'm trying to create this new 9 node. 9's next needs to be the dummy node because 9 is going to take the last position. So this statement creates the last node with its pointer initialized in the right place. Then we need to change the 5 node's next pointer. At the moment, 5 points at dummy and also 9 points at dummy. That's breaking the invariant on the singly linked list. We need only 9 to point at dummy. 5 needs to point at 9. That's the red pointer right here. So the tail changes its next pointer to point to the new node. So tail gives us this node object here. 5's next pointer points at 9. Now we need to move the tail because one of the invariants is the tail needs to point at the actual last node in the list, which is now the 9. Currently, the tail pointer is still pointing at the 5, so tail equals new node. Finally, the detail of the size, we need to increment size from 2 to 3, so we don't forget about that. This takes constant time because there's no loop here. These are all constant time statements. All right, now let's look at PopFront. This is the last constant time operation we're going to cover in this video. So the goal here is to remove the first node. Here's a before sketch in the top right corner. Let's say we have a singly linked list with 7, 1, and 4. The 7 is the first element. It needs to be removed, and pointers and sizes need to be updated correctly. First off, you cannot remove a first element if the list is empty. So we have an error check. If the size is 0, we throw an out of range exception. You can't remove from an empty list. If we get past the if, we know there's at least one node, and so we can legally remove a node. Again, I'm going to set up some pointers to keep the code clear. So dummy pointer would be tails next. Follow those pointers to get a pointer to the dummy node. Old front, meaning what the node that used to be the front that we're getting rid of, old front is dummy's next. That's based on the list invariant that the dummy node comes before the first element, and so dummy next points at the first node that actually has an element in it, which is 7 in the sketch. New front would be old front's next. So if I'm at the 7 and I go to the next node, that would be the 1. That's the node that will now take the role of the first element after we get rid of the current first element. So new front is old front's next. Now, dummy set next to new front. So what we need to do is change the dummy node's next to skip past the 7 and go directly to the 1. So we say dummy set your next to the new front instead of being old front. That's this line of code here. And then there's a detail that might go unnoticed, which is that it's possible for the PopFront operation to actually move what the tail is. It sounds a little backwards, but it can happen. That can happen if the list only has one element in it right now. When that happens, the front and the back are the same node. So if you remove the front and the list only has one element, that's also removing the back, and the tail needs to be changed in that case. So if the tail is equal to the old front, then tail is reassigned to dummy. This is doing pointer comparison here. So if the tail node is the same as the old front, we're removing the tail, then the tail changes to be the dummy node because that's how a empty singly linked list works. The tail points at the dummy node. Finally, minus size just to keep the size accurate. This takes constant time. It's a little bit more complicated. There's the if statement in there, but there's no looping, so this takes constant time. Let's look at an example of the case of starting with one element and becoming empty. It's a little bit maybe counterintuitive. So in the top right corner, that's what the list would look like beforehand. I've got a list with just one element, 7, so my size is 1. This is obeying all the invariants. The last node is also the first node. Its next pointer points at the dummy node. So if we go through the code here, the exception check doesn't happen. We set up the dummy node. Old front would be the 7 node. New front would be old front's next, so new front is also pointing at dummy. And then dummy set your next to new front, so dummy changes its next to itself. That makes dummy's next pointer a circular pointer that's just linking dummy to itself, which is correct. And then if we didn't have the if statement, tail would be pointing at this 7 node, which is kind of obsolete. It needs to go away. So if the tail is equal to the old front, then we set tail equal to dummy, and that fixes that problem. Now tail points at the dummy node. Okay, just to summarize, these are the operations on the singly linked list, and we've covered the first 5 of them that all run in constant time. The next video is going to cover the last 2 or 3 operations that take linear time.